What can I say? One of the best sections of Calc 1 is about to happen. We talked about it last class meeting, but now we're going to look at optimization problems, how to solve them, etc. So, without further ado, let me introduce this to you. The whole thing about optimization problems is you're trying to maximize something like profit, minimize something like material being used to construct something. A lot of things in nature and physics, path of least resistance for light rays and things like that. So a lot of things are based on that. In fact, I have three different examples in this section, and the third one I think will take on Snell's law from optics, which is what, physics 3 or something. It's really cool stuff. So let's begin this, but before we do, each video I'm going to follow kind of a process, and you should too. Once you get through graphing those functions, you got another world of work to do. You have to read and understand the problem. You have to identify the unknown quantities, determine their relationships, and then finally create a function that relates those guys together, those unknowns together. So a lot of the work is up front. What is the relationship? Because the rest of it is very mechanical. You search for the absolute max and min, and then you answer it. Okay, so most of it's up front, like any other word problem. Let's get to the first one. This is it's a good one to start with. You can see I chose from the textbook problem number 6 from the section, and it basically is saying, what's the minimum vertical distance? Did you see that word? Minimum. Underline it 100 times. Vertical distance. Vertical means up and down, right? Between the two parabolas, and here they are, this guy and this guy. The minimal vertical distance between them. Well, okay, how do you do that kind of thing? You know, these steps here mean I've got to come up with a way of relating them. So my favorite way, if it's a graphing problem like this, I'm pretty good at graphing. I hope you are too. Well, we're not all are at the same ability. But the first one, and in fact, I'll put this in red. This guy right here is y equals x squared, but he's bumped up by 1. So he is cruising like that. It doesn't have to be a perfect sketch. The other guy, maybe he'll be in blue. This guy here, I said blue, Mr. Blue Guy. Okay, this guy right here is x minus x squared. So I can tell it's drooping downward as a parabola, and it goes through 0 and it goes through 1. So it's probably, I don't know, something like this, let's say. Okay. The vertical distance they're talking about, and we can do this in green, I think, is from any point going up or down to the bottom curve, what's the minimum vertical distance as you scope it out? You know it's going to be somewhere in here somewhere, but we have to find it. So the way that you do that is you go, well, okay, what I want to do is come up with a formula for that. The top curve, well, let's do the blue curve. The blue curve is y is equal to x minus x squared. And this really takes time. Right now is the time-intensive part of these problems. Up here is y equals x squared plus 1. I know we all want them to go quickly. I'm so good at this. Well, the first one's the one that, this is the one you got to get on. So for vertical distance, you have to understand in this problem something about graphing. How far apart are they? You know what that is? It's the two functions subtracted one from the other. Wouldn't that be the distance? So like if you picked an x value here, you have an x value, let's say the curves are over here, and this guy's over here. And you pick some sort of x value, and you're going, okay, there's the one guy, and if I go straight up, I got another guy. Well, the y values are what we are comparing. The top curve has this distance, and the bottom curve, whatever color you choose, has this distance, and we're talking about the vertical distance between them. That's why you're going to say the distance equals the y1, which is, let's call it x squared plus 1. That's how big he is. He's the top curve, minus the bottom curve, x minus x squared, like so. Wouldn't that make sense? The x squared plus 1 is this distance here all the way up to him with any given x choice you make. And then the x minus x squared is this little guy right here. So the difference between them is their difference, literally. So I'll call this a function d, maybe d of x. It depends on which x you choose, you know. It's equal to, and if I clean this up, I've got x squared plus 1 minus x plus x squared, or d of x is 2x squared minus x plus 1. That function tells you how far apart. You give it an x, you give it an x, you give it an x, and it'll tell you, all you have to do is plug that x in, and that'll tell you the difference in the y values, or what he calls the vertical distance. And what are we trying to do? Minimize it. How do we minimize or maximize things in calculus? Look for critical points and then test the sign of the derivative. That's what we do. Let's do that. So the hard part in this problem is over, coming up with that equation. All right, so let's take this guy on. We'll say, again, I'll rewrite him one more time. This is the guy. And I'm going to look for critical points, and that means I'm going to derive it. That's the thing about this section. This is your function. You come up with this function, okay? And then you derive it, etc. So you're starting from scratch, from words and ideas to math symbols to models to now you're doing calculus. We get a 4x minus 1, it looks like. Critical point, of course, is found when you set it equal to 0. And that means x is 1 over 4. Now, typically, as you get confident, you go, I found it, I found it. But it's really good to kind of, all right, be careful now. Here is 1 over 4, and I'm going to test the sign of d prime to ensure that we have, what are we looking for? A minimum. All right, so let's test the value of this guy. If we plug in, so for example, what if we plug in 0, right here, 0 minus 1 is negative. It's going down. So far, so good. If we plug in, say, x is 1, we put a 1 there, we get 4, we get a positive. X is going up, the function's going up. So the distance between the two curves is drifting down to, it's getting shorter, shorter, shorter as we travel this way with x. And at 1/4, we found a minimal distance. So our last part of this is actually, last step, number 6, is answer the question, would you? And you would say, the minimum distance between the curves, I guess we can write that, between the parabolas is, and you could say d of 1/4 is equal to what? 2 times 1/4 squared, you know, minus 1/4 plus 1. And so that's 2/16 is 1/8, so minus 1, that would be minus 1/8. So I think we're getting 7/8. And that's the answer to this problem. Okay? There's some thinking going on, right? I got to take the curve. I have to draw a picture. I got to understand. But when you get to here and you feel confident, the rest is just gravy. You just do the calculus. Usually ends up being pretty nice. Usually. Not always. That's our first example. I have a couple more for you. So I will see you in the next roundup.